Okay, welcome to Guidesheet 3. This is on standing waves. Standing waves are a pattern that results when the wave is being reflected back into itself. What happens is the one end is a fixed end. The reflection coming back will be inverted, and you'll get the standing wave pattern as you can see in front of us. That pattern, if you consider this to be a fixed end, means that the reason we call it a standing wave is the wave no longer seems to travel from place to place. The individual parts move up and down. At an antinode, they will move the most. At a node, there are actually sections where the particles themselves won't move at all. So it's like a bouncing up and down upon each other. Alright, the positions along the medium that appear to be stationary are known as nodes. They are points of no displacement. The positions along the medium that are undergoing rapid motion are called anti or opposite to the nodes. And they will have opposite to the point, they'll have maximum displacement. So the nodes in this one, if we're labeling them in N, these are the nodes. And then these would be the antinodes. Highest and lowest peak, that section would be the antinodes, AN. And then nodes, again, are the places where we seem to get no motion. And then antinodes are the points where we get the maximum motion. Now, there's only really one antinode, so I don't have to draw both the up and the down, as I did in the first one. So node and antinode. So if we're counting the nodes and antinodes, here's 1, 2, 3 nodes, and 1, 2 antinodes. And here there's 1, 2, 3, 4, 5, 6, 7. 7 nodes, and 1, 2, 3, 4, 5, 6 antinodes. Each node is separated by a distance that is equal to 1/2 of a wavelength. Here is a complete wavelength. Here's the separation between them, that's 1/2 a wavelength. Here's a complete wavelength. Here's the separation between them, that's always half of a wavelength. Number 6, we're going to draw the standing wave pattern that would result if the strings vibrate the first, second, and third harmonic patterns. Okay, the first harmonic is 1 antinode. Now, that's distance here, this distance L, the length of this, therefore, is 1/2 of the wavelength. The second harmonic is 2 antinodes, so that's equal to 1 wavelength. And the third harmonic would be 1, 2, 3 antinodes, making the lengths 3/2 of the wavelength, so 1.5 wavelengths. Suppose the string in the above is 1.2 meters long, so that makes the entire distance 1.2 meters. We're going to calculate the actual wavelength. Now, if the 1.2 meters is equal to 1/2 of lambda, then lambda is equal to 2.4 meters. If wavelength is equal to, if the length is equal to 1.2 meters is 1 of lambda, then lambda is going to be equal to 1 meter. If 1.2 meters is equal to 3/2 of lambda, then the wavelength lambda is going to be 2/3 of 1.2, which is 0.8 meters. So with any wave, as the frequencies, the number of cycles goes up, the wavelength will go down. Okay, calculating some things from standing waves. We have a 1.5 meter string in the first one. It's vibrating at the first harmonic. The string vibrates up and down 33 cycles in 10 seconds. That's going to make the frequency 33 over 10, or 3.3 hertz. That's going to make the period equal to 1 over the frequency, which is 1 over 3.3, which is equal to 0.3 seconds. The wavelength, lambda, is going to be equal to 2 times the length of the string, which is 1.5 meters. So 2 times 1.5 is 3 meters long. And then the speed is equal to frequency times the wavelength. So that's 3.3 times 3, which is 9.9 meters per second. Okay, now no matter what harmonic we're working at, we're going to have the similar kind of mathematics for all of these situations. Here we're on the third harmonic, 3 antinodes, and the string is 6 meters, much longer. Don't compare it to the size above there, not drawn to scale. Again, it's 45 cycles in 10 seconds this time, so frequency is going to be number of cycles divided by time. 10 seconds, so that's 4.5 hertz. That's going to make the period be equal to 1 over the frequency, or 1 over 4.5, which is 0.22 seconds. Then the wavelength lambda is going to be 2/3, as we saw from the previous page, of 6, which is 4 meters. And then the speed, again, is going to be the frequency, 4.5, times the wavelength, 4, and we're going to be moving about 18 meters per second. Okay, here we have the fourth harmonic, which is 4 antinodes, and we have 48 cycles in 20 seconds. So we have a frequency of 2.4 hertz, that's cycles per second. The period, again, is always 1 over the frequency, so that's 1 over 2.4 is 0.42 seconds. The wavelength is going to be 2/4 of, or 1/2 of the distance, and this one is 5 meters long, so that's going to be 2.5 meters. And then the speed is going to be, again, frequency times wavelength, so 2.4 hertz times 2.5 meters is going to give us about 6 meters per second. Okay, so again, if you're not sure about this multiplier, you want to look at the number of cycles that you have, and it's going to be the inverse of that number of cycles. So we have 2 total cycles, inverse of 2 is 1/2. Here we're on the fifth harmonic, so we have 5 antinodes. And again, 21 cycles in 5 seconds is going to give us a frequency of 4.2 hertz, 4.2 cycles every second. That gives us a time period of 1 over 4.2, which is 0.24 seconds. Okay, so for wavelength, we're going to be at 2/5, 5 cycles in the harmonic, fifth harmonic, and we're going to need to multiply that by the length of 8.2 meters of the whole string, and that's going to give us a wavelength of 3.3 meters. And then finally, again, the speed is frequency times wavelength, so 4.2 times 3.3 will give us a speed of about 14 meters per second. Okay, so these are the 5 harmonics you're going to be making and using in this what we call the snaky lab. It's essentially a long spring that you're going to take and stretch out to a consistent length. So instead of the lengths changing as they did here, the length is going to be consistent, but you're going to make different harmonics. So you're going to have to measure your frequency for each of the 5 harmonics and then kind of go through the same mathematics to figure out your various elements of the standing wave. So that'll be coming up soon, so be ready for that. And that's it for standing waves.